And speaker. So the second talk is also given by a visitor. So Nguyen, original from Vietnam, and Tree did his PhD at MIT, and I think graduated about 2 years ago, and now 1 year ago. Okay, I'm sorry, just so last year.
Yes.
Oh, okay. Okay, so he just graduated less than a year ago, and now he is a postdoc fellow at Northwestern as a Sierra fellow. And Tree works on using machine learning techniques to study the nature of dark matter. So today he can talk about some of his work probably associated with his PhD thesis and also some work he's doing at the postdoc time at Northwestern. So Tree, please take it away.
All right. Hi everyone. So I'm Tree. I'm from Sierra, Northwestern. I'm also affiliated with the NSF AI Institute for Artificial Intelligence Fundamental Direction at MIT Harvard, as well as the very newly funded science NSF STEM Institute at in Chicago, Northwestern universities. So I mostly work on using stellar kinematics to understand the distribution of dark matter in the universe. And today I want to mostly talk about this work. Using simulation-based inference and GraphNPE network to do so. So just a little bit of background that we have very good understanding of the cosmology and the universe on a very large scale with the CDM models. But typically when you go to like galactic, subgalactic scale, like North galaxies kind of scale, you start seeing like discrepancies between observation and expectation from the CDM. So here are a few examples of the so-called small-scale challenges in the CDM is a satellite to need to for content diversity problems. So all these are fancy names, but pretty much what all they come down to is like the discrepancy between observations of the distribution of dwarf galaxies, satellite galaxies, near the Milky Way or local group galaxies, with expectation from simulations from the CDM cosmologies. This is satellite satellite plan problems typically deal with the distribution of like how the mass function, how the spatial distribution of the satellite galaxies are different from what you see in simulations. While corpus and diversity problems typically deal with the inner structure of the galaxy itself, like the inner density profiles of these galaxies. And one thing I want to stress is that it's very uncertain if baryon feedback and baryon effects in general can be like the foolproof solution for all of these problems. So say, for example, this is satellite problems is like the one that always solved. And you can like kind of alleviate that with like better like models of baryon feedback or better just understanding of observational bias. But not all of these models can be solved with baryon feedback models. And it's motivate a lot of alternative dark matter models. So within, say, the Milky Way, so this is the Andromeda galaxies, but let's just pretend this is the Milky Way, right? So you can actually do a lot on the galactic subgalactic scale to like understanding and studying the distribution of dark matter, and the nature, properties, nature of dark matter. Say, for example, if you look at the galactic scale, or even the solar neighborhood, you can kind of like measure a lot of the interaction between dark matter particles or dark matter particles in the barrier. These are also called direct detection, dark matter. So you can kind of like study these like at the center or like even the solar neighborhood. Like, but what I usually focus on is to see if you can use dwarf galaxies or stellar stream, which are a accreted structure from like satellite galaxy accreted onto the Milky Way or like the host galaxies, to see if like whether you can use the stellar kinematics of these galaxies, dwarf galaxy and stellar streams to kind of like propping the underlying distribution of dark matter, which is sensitive to the dark matter particles nature. So I work on both of these, but mostly what I want to focus on today is on the dwarf galaxy scale, like stellar stream. But feel free to talk to me about stellar stream later on. So what are dwarf galaxies? So dwarf galaxies are typically very small galaxies, and they can be found in isolation. But most of the time, we can find them as like satellite galaxies of the Milky Way or Andromeda or like any other, like big galaxies, host galaxies. They're one of the first galaxies to form. And the thing about these galaxies that they don't have a lot of stars, they don't have a lot of gas, right? So like either the star, the gas has been really stripped, and they form down like by the host galaxies. This is an example, it's a little bit blurry, but this is an example of a satellite galaxy, dwarf galaxies. that's observed by the Hubble Space Telescope. And you can see that, this look nothing like the Milky Way, like this galaxy you usually see. Like this is one of the brighter one. And you also don't see a lot of signatures of galaxy formations stuff in here. And in the Milky Way, there's roughly 50 satellite galaxies that have been discovered that will give minus. When talking about these galaxies, those galaxies, I'm mostly talking about the mass scale of 10 to the 9, 10 to the 11 solar mass. But the stellar mass can vary by the 7 orders of magnitude, from 10 to the 2 to 10 to the 7. So very wide range of stellar mass, but very narrow range of dark matter halo mass. And one signature of studying dark matter in both galaxies, the dark matter density mass density profiles in these galaxies, because the nature of the profiles itself, the shape of the profiles, can inform you about the nature of the dark matter particles. But at the same time, a good understanding of the dark matter density profiles can give you a good expectation for how much dark matter should be interaction with each other, and that can help you constrain things like the annihilation rate of dark matters. And that leads to interaction protection with dark matter. So these are a very pristine system that very dark matter dominated that you can use to study the nature of dark matter. And when you typically look into just trying to inform the density profiles of these galaxies, and this is kind of debatable, but this is a problem, but this rising tension with the corpus. But what it is that let's say if you have density and so on masses and radius, radial distribution of the density profiles. Typically, people would use this generalized form of the NFW profile, the very and white, to kind of study, to kind of fit these profiles. Right? And usually there are typically two solutions that you see people talk about, the custody profiles and the core profiles. So when NFW fit these profiles on all of the dark matter void simulations, what they found is that pretty much all dark matter halos kind of follow this very custody profiles in the cold dark matter universe. Right? So and typically you see people referring to this when you have only cold dark matter with little to no baryonic feedback. But with the core profiles, you see in the lot of galaxies that it can have very constant density core. And this could result from baryonic feedback kind of pushing out the distribution of gas and star, which in turn pushing out the dark matter profiles. So baryonic feedback can flatten out into a core. But alternatively, the baryonic feedback is not the solution. You can kind of invoke alternative dark matter models by step interaction and let the dark matter particles exchange energy with each other. And in those cases, you can also fluffing out the dust into a core. And the problem is that in many of these dwarf galaxies, when you don't really have signature of star formation, when you see little to no gas, right? So you don't expect baryonic feedback to play a role. You would expect them to have the very positive dark matter density profiles. The problem is many of these, you actually see a core profiles, which is kind of perplexing because how do you create a core profiles in a galaxy with little to no baryonic feedback? So that's why it's more debating on the alternative dark matter models. So I want to go a little bit into how people typically do this, right? So you need to get the density profiles out somehow. Right, and you can do it with gas and middle rotation curve. There are still some gas that you can measure in some isolated dwarf galaxies. But most of the time, what people do is people would look for resolved stars, and they would measure their line of sight velocity, so kind of stellar kinematics, and they use Ching's equation to try to map these stellar kinematics, mostly the velocity dispersion of the system, go to the gravitational potential. And then from that, you can calculate it to dark matter profiles now. And this is a very intimidating equations. It's the Ching's equations. But what it is that you can kind of think of it like some kind of pressure term, that related to some kind of mass profile. So that's pretty much what it is. And it's kind of related to this, gravitational potential to the so-called radial velocity dispersion profile in the system. And simplified version of that, it's still not really one-to-one. If you want to look at this, you have to make a lot of assumption. But if you want a very simplified version of that, it's just dispersion mass relation, right? We have dispersion gas of stars in like a self-gravitating system that you related to the mass. And this term here is very important term. It's called the velocity anisotropy profiles. And this is kind of like one of the biggest problems, which is dynamical modeling. I will go over a little bit later. But what it is that it's kind of a measure kind of an anisotropy, so that the relation between radial and tangential velocity dispersion. Because typically in a self-gravitating system, when you only look at projection, you don't really have velocity dispersion profiles. So you need this velocity anisotropy difference to kind of like relate it to tangential and radial velocity dispersion. And this example, how change the equation is developed. So typically you only have access to line of sight velocity and to be able to check the coordinate of the galaxies. And under the unusual system, Jan and Sid in 2022, they show that with only line of sight velocities, if you really want to constrain between core and custom derivative density profiles, you need at least 10,000 stellar tracer. And this is agreed with like a lot of the past studies, the string slope. And this is an example of like a Honda plot where they try to fit the generalized NFW profiles. Where this is the density, this is the scale radius, this is the view slope, and this is for only 100 tracer. And like if you focus it on the linear slope itself, then this is like 7.47 plus and minus 1. So like how do you constrain corpus viscosity if your error bar is plus and minus 1? So you can't. And choose equation also have tons of problems where the assumption of spherical equilibrium and spherical equilibrium kind of breakdowns when occasionally when you have like isolated galaxies that still within this like pre-thin star formation cycle. And yeah, so like assumption of dynamical equilibrium with spherical symmetry is typically a problem in Chio's equation. But what really fundamentally matters, even if the galaxy stands by all these assumptions, is that the fact that you only have the projection, and with only the projection, the velocity dispersion is like terms within the Chio's equation, which is I put here, kind of like creating problems. And this problem is the so-called anisotropy degeneracies, where you can have the same line of sight velocity dispersions that can be explained by a very isotropic velocity dispersion with very high enclosed mass, or very small enclosed mass, but very radially anisotropy velocity dispersions. So there's a very big degeneracy between this mass term and this terms here. When we try to relate the velocity dispersion. And there's multiple ways you can like kind of solve this that unfortunately I don't have time to go over. But one of the way that I think is pretty elegant that you can solve this is to actually just remove this reliance on velocity dispersions itself. So what the velocity dispersion is that it's a second moment of the so-called distribution functions, which can describe the phase-space density, the phase-space distribution of all the traces stars. So like this is like X and B here, it's like 6-dimensional coordinate, like between velocity, between the positions, right? And the velocity dispersion is basically the second moment of this curve, right? So if you can actually use this distribution function directly into your inference process to try to get down the profiles, then you will remove the reliance on sigma, and hopefully you will be able to solve mass anisotropy degeneracy. But the problem is that this term is also very complicated, right? Even with projected coordinates, it's like a 3D, position plus line of sight velocities for multiple traces stars. It's not a very, easy thing to like really incorporate into the inference process. And people have actually tried to do this, and usually the process is very slow. And also there were tons of problems where they're dealing with like actually missing data. It doesn't mean the distribution function here. It's mostly defined by 6D, so like to convert this into like 3D, like one like lots of velocities with projected coordinate. It's not a very trivial thing. So that's why I turned to machine learning. So machine learning, what you need about machine learning, and machine learning can deal with high dimensional data, very complex kind of data, very, very well. And we deal with like very complex and high dimensional problems. So why not trying to use machine learning to do this? And like specifically what I want to talk about today is a set of techniques for simulation-based inference that can incorporate the simulations directly into the inference process without explicitly defining the likelihood. And simulation-based inference is very commonly used actually nowadays. It started to like kind of pick up right like 2021. And like all of these work in like both cosmology, as in the physics, gravitational wave, strong lensing, and like only a few cosmology people start to be able to use it. And for review of it, you can look at like paper 2020, as well as this link here from Cindy Sharma. It's like pretty much like most of the simulation-based inference paper in it. And specifically simulation-based inference, there's a lot of, there's some technique in it. And what I want to talk about is the so-called neural posterior estimation, where you're trying to use a density estimator neural network to try to get density profile, so the posterior estimation directly. So typically how it works, like traditionally, let's say traditionally, you want to do this analytically, how does it work? When you would define a prior distribution, you would write out the likelihood, and then you use MCMC or necessarily some kind of Bayesian sampling technique to kind of like sample this posterior space. With simulation-based inference, or NPE specifically in this case, what you have is you still define your prior distribution, but then you have the simulations. And what your simulation is that your simulation will take in this underlying parameters theta, which is, let's say, in my case, the dark matter density profiles, and give you the observables, right, like the data. But so in a way, your simulation is kind of like a likelihood. Your simulation is a likelihood. Usually, it's very tricky to incorporate directly into the inference process. With machine learning, it's a little bit easier to do so. So you have to prior. You sample, a data set from an example, simulate, put into simulations, get all the observable from that data set. What the neural posterior estimation do is that you have an NPE, which is kind of like a very good way to like model like density distribution in machine learning. It kind of like repeat a combination of theta and x and theta and x, and with enough training data, like what it does is like kind of like roughly estimating the implicit, p, theta, and x. That's what it basically implicitly does. So like, given enough of these combinations, it should be able to like directly give you the zero estimation, and I can go like much more in more detail about NPE later on. And this is pretty much like a training process, right? So like you keep feeding the data until like it's like learn enough forward to enough to like learn this density. And inference given some kind of observable data, we can directly sample from this. So another advantage of this compared to like say MCMC-based methods is that this is like fully amortized, meaning that if you change your observed data, you don't have to rerun the entire framework. So I want to go into a little bit into the simulations. So previously, I say that we want to try to use this distribution function directly into the inference process. But what the distribution function is, that is defined in phase-based densities. So in a way, your distribution function can also be treated as simulations, right? So given a set of, like parameters of interest, a set of just equations. So everything I do with equations, right? And after the equations, some kind of numbers, stellar density profiles, like also combinary stellar velocity distribution. Like with all of this, I can like write out equation, view out my distribution function, and I can sample from that distribution functions to get my galaxies. Right? This is one of my galaxy sample. And the advantage of this compared to, let's say, training this directly on hydro simulations is that you know exactly what you put into it. Like I know that what my neural network learning is this likelihood here, that this just directly this distribution function itself, right? My likelihood is literally just evaluating this distribution function, at every single point of the tracer coordinate. So just kind of like put everything together. You have your power distribution, simulations, you feed it everything here. So you have the galaxies. What you do is usually, you want to feed this galaxy directly into some kind of the estimator is like normalizing flows, which is a very common test we use in machine learning. And I don't have time to go over it. I can talk about it later. But in reality, what you also want to like advance this data because it's a very high-dimensional data. So like with machine learning, everything is like like just depending on like your data and your architectures kind of depends on each other. So you just use a graphic network to like condense this entire set of data into these features and you can feed it in. And with this whole framework, you can like get the posterior distribution out. So I think I'm running out of time. So I'm going to skip the slides, but this is an example of what you can get out of the models. You don't have an estimate that have like the entire posterior distribution that can outperform. But it's not very interesting to look at like result and training data because ML models tend to break down, out of distribution. So you want to like stress test on the more realistic galaxies. So the second paper is basically what we exactly do now. We take all the satellite galaxies from the FIRE-2 actual simulation, so very realistic environment. So all of these satellites we extract out of FIRE-2 simulations, and we test the density profiles on it. And this is an example. So as a reminder, the simulation has nothing to do with HyperSim, right? And here I'm showing the density profile for a few examples. The galaxy, they should be spanning all different galaxies. See here, so the flat data point of the truth. And the orange is the what our GraphNPE what we are like creating. Simple cheese is like a very simple cheese framework. And what I do is like usually very high tracer like the methods kind of converge to each other because at high level tracer cheese become more flexible and I can definitely talk about it later. Very low level tracer, which is like reaching the limit of like ultra faint dwarf galaxies, the methods like have a much better screen. And we also compare this with like more advanced method like GraphSphere from just in nature. And this is like using higher order moment. Methods like do constrain, and the methods is like very has a very comparable performance, even though ours has like typically has more advantage at like tell, and also like machine faster. And to set the other two results is the maximum circular velocities and the pre-infall mass. So we're trying to see if we can get the Vmax and M200 out. And these are very interesting quantities if you want to try to do cosmology with it. This is an example. So we test also all of these galaxies, and we also divide them into like orbital parameters fit. So each of these kind of like measuring all pairing versus the R200 on the host. And this one is like the least least tabulate disrupted bin, and this one is the more tabulate disrupted bin. And so just the proximity is the paracenter. Consider everything like constrained like pretty well for the ends. For M200, so the truth is in x-axis, and the y-axis is the predictable. Yes, and this is the first test with astronomical methods that we do on a very realistic environment to like extract Vmax and M200. And I'll skip the caveat slide, and I'll give my takeaway here, and I'll answer any question.
So I don't think we'll have time for questions, but she will be here all week this week, and you're welcome to talk to him. He is at the visitor office, AB123, and also he talk about dwarf galaxy today. I think he will give a talk on the stellar streams at my group meeting this Friday at 1 p.m. in AB113 for anyone who's interested. But feel free to reach out to Tree for the rest of the week. He will be here all week this week. Yeah. Okay.